strontium ion, I put it in here with water in this volume, and then I say, if I keep adding one or the other or whatever, can I precipitate that out? We're going to talk more about things other than water, by the way. Did you guys do that in lab also? Where you mix it with certain things to make complex ion formation? Yeah. Okay, so that's
Saturated in water
or say ammonia or whatever.
Oh, cool.
So that's another thing that we'll get to. But here, all I'm saying is I just want to precipitate out one or the other by adding a certain amount and then precipitating it out. So let's take a look how we do that. Okay, so I have here the KSB for barium chromate and for strontium chromate. And the first thing I'm going to identify here is the what does this KSB mean for each one?
How much of it's given.
The solubility?
Or it's going to tell you how much it'll turn to ion.
The molar
Yeah.
solubility?
It will tell you the ion amount, right? So I'm looking here, I'm just saying that the KSB for the first one is going to be Ba2+, and CrO4, 2-, I think, like this, right? It's the concentration of this times this. I want to make sure that's really, really clear, because once again, you got to make sure if you're not clear on what you're looking at, then do the basics that you already know. This is something we did at the very beginning of the semester, right, where we just looked at what, for example, Ks are. And then this KSB then is going to be what? It's going to equal to the Sr2+ and the chromate, right?
Mm-hmm.
So the first thing I'm going to say is what's similar to both?
Oh, the
They
chromate?
have common ion chromate.
Yeah.
They both have the chromate.
Yeah.
Okay, so that means that I have the barium and I have the strontium. I have the chromate in both. All I'm saying is how much of this do I add to precipitate one and leave the other one in solution? Because that's what's binding. So if this one here, is this one more or less than this one?
The barium is less than that.
This one's lower, right?
Right.
Okay, lower. Relative to each other, higher. I'm going to get you out of the numbers here for a second, just to visualize this with, I have one that has a lower KSB, one that has a higher KSB. What does that mean?
These
One
are,
is more gonna ionize easier than the other.
yeah.
more dissociated.
That one will stay more as a solid. This one will dissociate.
Interesting question, right? Which is why I'm proposing it.
Yeah.
Okay, this is lower, which means what?
It would
It's
dissociate.
not gonna ionize.
Less of this will ionize, or what else can I say? If I have the same amount, so let me do this. I have the same amount of these, so I have 0.1 molar of both of those. Okay, so that stays the same. So now I'm just changing this.
Chromate, yeah.
If I put in a certain amount of this, let's say I put in 0.2 molar, okay? Then these two numbers will add up to something, and these two numbers will add up to something. And what does that do compared to this and this? You see what I'm asking?
Yeah.
So then if I think of it that way, then this one here, I need less of this to precipitate this compound, right? Is one way to think about it. And I need more of this to precipitate this one.
Yeah.
In that context, then, it's pretty obvious now, since this is lower, this is higher, this one should precipitate first. So I only need to add enough chromate. I think they told me before on the previous slide it was 0.1, that's why I used it here, I'm assuming?
Yeah.
Just going, okay. So this is 0.1, this is 0.1. I only need a certain amount of chromate, and I could precipitate, and I'll only form this amount, so the rest will precipitate out. Yet this one will still stay in ion form. They haven't precipitated because I don't have enough chromate in there for it to come out of solution. Does that make sense? So now when you look at the numbers, now it should seem a little easier. This is much lower, this is much higher, therefore this one's going to precipitate out before this if I could put enough chromate to precipitate this, but not enough to precipitate that. And that's all I'm doing there. That's the selective precipitation. I'm selecting a certain amount of the, in this case, of the anion to precipitate out a cation.
So
And not
the
enough.
KSB on the barium be lower than the strontium one? doesn't mean that it's harder to precipitate, it just means it's gonna precipitate less.
It means that within the volume that I have and the amount of the barium I have, I don't need as much strontium and it will precipitate out.
Okay, but it doesn't make it any harder, it just precipitates.
Well, that's because its ability, how they're interacting, right? So it does make it harder, right? Because there's some interaction there between the barium and the chromium. In this case, though, that type of interaction is an ionic compound.
It's kind of like an
So
affinity.
you're looking at the ionic formation of that compound, and it's easier for this one to bind together than it is for this one, if in the way you're stating it. And that's represented by it, you need a lot less of this here to precipitate out than this one.
Okay.
Another way to think about this is that the solution's just too dilute up until that point, right? They're not close enough and able to interact together. The same, so what we've done here is I'm listening to these questions and thinking about 101 and projecting it into this is, in 101 we just talked about double replacement reactions or aqueous reactions, and we just said this thing precipitates out and it's 100% and whatever else, right? And then in a separate section we talked about dilution and saturation, and now I'm really putting them together, right? And I'm saying that at this amount, it's saturated. And in the same volume, I need more to saturate this one.
Oh, okay.
It's coming out of solution.
Okay.
That's right, and I think we talked a little bit at the end of last lecture about saturation, and does that put it in a different light?
Yeah.
We really never connected those two things as I'm listening to the questions before, and we still don't hear, so I'm going to make that connection. We're really just looking at if I put a certain amount, let's just take something simpler. Here I'm making something, but let's just say I take sodium chloride, a solid, and I throw it into water. And I throw it into, say, a cup of water. Say I throw it into this volume here, whatever he has here, okay?
Right.
At some point, I'm going to throw enough salt in, I'm going to put some in it, and I shake it up, and it's going to dissolve, right? It's going to ionize. It's going to separate into sodium and chloride. At some point, I'm going to put so much in that it's going to reform into sodium chloride, or that's not how we thought about it before. It just saturated. And now if you think of it in that term, you can see what's happening here, right? And that's the connection between, and that's why we talked about saturation early on in this chapter, or Tuesday. When you put it in that context, you start to see it a little better. You're just talking about at that amount, it's just saturated in that volume. Right? Everybody see that? So that's just you could think of it either way, really, because they're kind of the same thing. But that should put it into light if you just think about adding something to your own solutions at home. I have water, I throw in some salt, I want salt water. Maybe I have tea and I want to throw in sugar. Right? If I throw in enough sugar, it's not all gonna dissolve.
What is dictating the reason why one would actually use less than the other one? It would be more
Because
mass?
they have, that's what Taylor was asking, right? Is that they have a stronger connection. They're going to form they have a stronger connection. You need less of it to interact to form that bond. And then it precipitates out. It's
Stronger
easier,
connection.
or you could also define it as it's easier to separate. One thing is easier to separate, or you
okay.
could think of it as one thing is easier to form. Solubility, KSB. What I haven't got to and I will get to, formation, KF.
Okay.
You could think of it either way. One thing's either easier to form or harder to separate. Okay? And those you need numbers, you determine those things experimentally, right? It's not like you could just look up on the board and say, oh, it's going to be this or this.
No, but trying to understand.
Right? That's what
put it
I'm
into
saying, though.
perspective.
It's that these are ionic compounds. So you're just saying that from your experiment and observations,
Right.
this forms quicker or with less of it than this one. This KF is higher, this KSB is lower, or whatever the case may be, accordingly. Right?
Observation, right.
Okay. And that's how you determine a lot of these things. So does that put this in perspective a little bit? Go
So
ahead.
just to clarify, you're saying if they're easier to separate, then they can form the precipitate?
No.
The other way.
If they're easier to separate, you have a higher KSB,
So more ions.
more ions.
Oh, okay.
Right. If it's easier to form, then you have a higher KF. Yes. Right? Does that make sense? Okay, so here, first precipitate, this is going to precipitate out first. and then this will precipitate out second. Now, if I add too much chromate, they'll both precipitate out. I can't separate them. So you got to keep that in mind too, right? I don't want to add so much chromate to this that I separate both. So I need to stay underneath this amount and above this amount. I don't want to. If I don't have enough chromate to precipitate either, they both stay in solution. If I have too much, they both precipitate out. I need to find just above one and just below another, which also means that if these are too close, that would be almost impossible to do, right? Because I'm going to have some overlap, and then I couldn't say I have all of one or all of another. Okay.
Oh.
Now, how does this put? What's up?
No, we had that in lab, and what's his name? Jose actually had to come in and test it because we were getting false positives on the barium chromate because we added the potassium chromate to the solution, to the unknown, and we thought we were getting the barium, but then he did it separately, and then he had to rerun the whole test again to find out that there was actually no barium, that it was actually reacting with another one.
Oh, something
It
else was
just
in there.
putting too much.
So
of it.
yeah, there's something contaminated.
Right.
Yeah. So here, all it's saying is that I need a lower amount of concentration of chromate to precipitate out the barium than the chromate I need to precipitate out the strontium. That's all. That's nothing different than what we just talked about.
Nice. That's cool.
Okay. Now here, this is kind of an interesting thing, and there's something subtle in here that, not something you'd actually get on an exam, but something I should just mention. So this says these two ions can be separated, and that's of course the whole thing we've been talking about here. By adding a concentrated blah, blah, blah. And it says here this term.
Slowly.
Slowly.
Yeah.
Because when you're doing this, generally let's say you have an Erlenmeyer flask with your barium and your chromate and whatever in it. And that with just water. And now you're putting in from a burette, you turn the stopcock and you release some potassium chromate. If you recall, you did that in titration experiments with a strong acid and a strong base or some kind of thing like that, if you recall, right? And you had phenolphthalein in there and it would turn pink, right? So what you had usually was an acid. The phenolphthalein is clear in the acid. You have a base up in the burette, you let the base down. And if you notice, right where it came down, what happened? Change color. And then what did you have to do?
Sure, yeah.
Shake it up, and then it distributed throughout. So what happens if you put too much in too quickly in one concentrated spot?
Oh, you'll get resistance.
Yes. You would end up precipitating this as well, because you have so much at that point. You've overwhelmed it, and in that isolated region within the area, you're going to see some of this form because there's a lot of it in that area. So once again, and then if you shake it out, it depends on how hard it is to take out at that point. It's not quite the same thing as just getting rid of the indicator, phenolphthalein, right, in the
That's
the
why
pink
we
color.
centrifuge.
Yeah, so it might be a little harder to do that in this case. So that's why I'm emphasizing if you were doing something like this, you want to do it slowly. And once again, slowly is relative, right? But I mean, this doesn't mean turn it on and let it just blast through, right? Slowly can mean it doesn't have to also drip, 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 drip. But when you're doing it, what can you do if you wanted to turn it a little faster and you just wanted to be safe? Swirl it. Yeah, absolutely. Something like that. Just to keep in mind what's happening at, from a micro position within the total body of the liquid.
Mm-hmm.
Okay. So now let's see how this works here. I have magnesium and calcium ions present, and they're in seawater. So that's interesting. There's some salt in there. And these can be separated by the addition of potassium hydroxide to precipitate these two things. Okay. This has a concentration of this and a concentration of that. Okay. So the KSBs for each, given here. So my very first question then, of course, just evaluating this, what am I going to precipitate out first?
The magnesium?
Okay, that should be really, really obvious, right?
It's so much lower.
It's so much lower. So I need a lot less of the potassium hydroxide to precipitate this out. But I also have different concentrations here, right? Okay. What's that? This is a lot more.
Yeah.
In terms of the magnesium ion versus the calcium ion. Okay. So based on the given information, which ion precipitates first? Now, I did point out something there, though, right? They are starting at different concentrations.
Right.
Yes.
So that could have been a problem here. We didn't account for that. right? And that's probably something I'm not gonna over stress or make you guys too concerned with on an exam. However, you should consider that, because what if this, so this is not, this is to the -6, -13, what fold difference is that?
Like,
It's a lot,
Almost twice, yeah.
right?
Yeah.
10 to the 7th?
it's like,
That's a lot. So clearly that difference isn't gonna be accounted for here, right? Which is why this stays. But what if I did have something much, much lower here and much, much higher here, or vice versa? Then it could be a difference, right? And then it might not necessarily fit this scheme, just looking at the KSP. I'm not, once again, not gonna give you that kind of thing, but I want you to think. I want you to be aware of those kinds of things, right? Because in the real world, if you're doing something and trying to figure something out, it might not be so nice like this, right?
Right.
These are always put up with the perfect scenarios just to explain it. But in reality, you don't know what you're gonna get. And sometimes you have to account for things that maybe we didn't teach you in a lower level class. Okay. So then, was that the first question? That's all the first question was about?
Yeah, which one was first?
Okay. Yeah, so that's pretty easy, right?
Mm.
All the questions should be like that.
wish.
Here's the second part. What is the minimum hydroxide that is required for the first ion to precipitate?
3.49 times 10 to the
That's
negative
pretty
12.
concentration.
Yeah, now the concentration matters, right?
Yeah. 0.059.
So what am I gonna do here? What's the first thing I need to do? What, if I'm sitting in a chair on an exam, what would I do here?
The
That's the
equation.
equation, right?
Yeah.
What's the equation here? Magnesium,
Magnesium
hydroxide forms
magnesium and hydroxide.
magnesium ion and 2 hydroxide ions.
Right.
That's why you make the equation. There are 2.
Right.
You wouldn't know that and see it unless you wrote out the equation, right? Now, okay, so maybe I should do that on the sideboard, since they're assuming you guys already know this, as though this is gonna be that simple. So what I'm really saying is that I'm actually forming it here, but generally, you look at it as you've already formed 100%, and now you're going back to see what you have left. So let's pretend like we've done that, and we have now magnesium hydroxide, and this is gonna be a
Aqueous. Solid.
solid. That's kind of important here, right?
Mm-hmm.
That's a solid. And then that goes to some equilibrium, which gives me
Mg2
Mg2 plus 2OH
aqueous.
minus, and there's that 2 I was talking about. Drawing that out and seeing where you're at helps.
Yeah.
It puts it in perspective and you don't miss that kind of thing, okay? And hence that's why you can't follow everything between KSB and molar concentrations, if you recall. Because sometimes they come out like this, so there are 2 of these for one of those. Okay, so we've done that. So then what's the KSB here?
KSP is 2.06 times 10 to the negative.
I have magnesium 2 plus, right? And I have what? 2.
OH to the second power.
Okay, so so then if we're just gonna say concentration, let's do that. OH minus squared, right?
Right.
Now, did I start with something here?
Started with the 0.059.
I started with magnesium,
Uh-huh.
okay, what was that?
0.059.
0.059,
Yeah.
Yeah.
okay? And then I was given a KSB, what was that?
That's 2.06 10 to the negative 13.
Okay,
Mhm.
and then here I don't know, so this is gonna be what?
That's gonna be X.
X or
And minus X. Oh,
2X?
yeah, 2X.
That 2 is important, right? But if I'm solving for the concentration, do I care about this 2 here?
No.
This 2X is the concentration of it,
Right.
literally. Okay, so that, in that case, then, let's just leave this as OH minus, because that's what I'm solving for.
Okay.
Okay. Now let's see what happens up here. What did they do here? What did they do with this equation here?
Divided 0.059.
So they have the KSB, they took this and they divided it, right?
You get 3.49.
And they left this here, so now I'm gonna move this over here, okay?
3.49.
But then this is squared, so they square rooted that, and they square rooted this. Does that now look like what they have up there? And that's all they did.
1.86
So let's take a
or
look.
87.
Ah, there we go. This should look just like this, and it does. And now they just solve for that,
10 to the
and that's my
negative
hydroxide. What does that tell me? What does that mean?
You need that much molarity of
hydroxide to
That's the
precipitate.
concentration in terms of molarity of the hydroxide that I need
To
to
precipitate.
precipitate
The magnesium.
this amount of magnesium. Absolutely, yes.
Cool.
When you understand what it means, it makes a lot more sense, and then you don't have to just try to memorize how these equations work, right? You just solve for the equation. It's just an automatic because you understand what's happening. If you try to distance yourself and just say, oh, if I could figure out which equation to match the solution, then you don't really know what's going on, and that's where you start making all kinds of mistakes. Am I using KSB? How does KSB work? Am I using something else, KA, KB? What am I doing? But if you understand what you're doing and you rationalize it out, you don't even need your cheat sheet, right? Because it's automatic, which is exactly what happens. You have a cheat sheet, you wrote these things down. If you don't know what to do, or you get nervous and your logic breaks down, you start trying to just grab one thing to make it fit something else, right? It's like putting a hole in a square. You're not always gonna fit, it's gonna get all over the place. And you kind of know that. You're like, oh, I don't have enough time, I'll just do whatever and hopefully I get something out of it. But if you already understand what's happening, you never even turn that sheet. Because you rationalize it like this in your head and you work it out and then you say, okay, this is the answer. If you want to go back and say, is this the right kind of thing? Oh yeah, it's right there, right? So you want to go the other way if you want to check most of the time. If you're trying to use that cheat sheet for these, the cheat sheet should just help you organize your thoughts and give you that security blanket. But if you're using it on the exam, you're probably in trouble. That's what I'm going to suggest. So, you know, it just makes you feel good, but it doesn't necessarily help you. It might help you on one or two problems, but then it's going to hurt you on others because now that's what you're trying to do. You're trying to associate things, right? Okay, so this tells me this. I'm sure what's the next question going to be?
Oh, it's actually a little bit different. It doesn't tell how much of the OH you need for the calcium, but instead, what is the concentration when calcium actually precipitates?
So we're looking here. This
You
is
gotta go.
essentially what we started with. We
Gonna go
just
back
figured
and
out
forth.
how much
Gotta go back
hydroxide
to
it takes to precipitate this amount out, which means that that amount presumably is still keeping the calcium ion
In ions.
in the solution, right? Okay. So now it's probably going to say, well, now how much of this do I need, or at this amount, what do I have here, and that
Yeah.
kind of stuff, or how much, you know, something along those lines. That's most likely where we're going with it. Okay, so the first one we have, now the second one. When the concentration of calcium begins to precipitate, what is the magnesium concentration?
So you gotta get the concentration of the hydroxide, plug it into the other one.
Okay. So what did I do here? Same kind of thing I did over here,
Mhm.
right?
Is it the magnesium concentration zero? It's all precipitate.
Magnesium concentration should in theory be,
Higher.
what are we putting in? Let's go back and take a look at what we're putting in here. So remember, this started to precipitate relative to this amount, right? Did that mean that all of that precipitated?
No.
That's where it started to precipitate.
Right.
So some magnesium is left.
Yeah.
Is that okay? That's a good question, though, actually. You know, that's something that a lot of people may not have thought of. And so now, when I'm adding more hydroxide at this moment, I'm now starting to precipitate out that. Remember, the hydroxide we found was just where it started to precipitate, right? So now, when I find how much it takes to precipitate this, I could then say, well, then how much of that do I have left? That's essentially what this question is asking. A little bit different, so that is a little odd, right? The style of question. Once again, if I'm in an exam, I got to think about those things. What is it actually saying? Now it's not so easy just to grab an equation and throw it up there. The first thing I have to do is what? I have to figure out, well, what is that minimum hydroxide required? Oh, this is B. Okay, so that's, by the way, this says minimum required to precipitate the first one, so that's an important, right, piece of information. Here it says when calcium begins to precipitate, once again, that beginning, then what is magnesium? So first I need to figure out what it takes for the hydroxide to start precipitating the calcium at that calcium concentration,
Right.
right? Then I could say I could take that amount of hydroxide back to the other equation with the magnesium and see how much magnesium I have left.
Right.
Okay, so you just subtract it?
That would be the strategy. Let's take a look. Not necessarily, right? You just put it back into the equation and see where you're at, right? Because now I'm saying that I'm taking out what I started with the barium, right? I'm now putting in the concentration of the hydroxide with the KSB, and now seeing what I have in the barium left. Okay, so here, hopefully this looks okay. Everything okay so far here? Oops. Well, look at that. This all of a sudden allowed me to do this. Cool. Have a new toy. We don't get many new toys over the years, so that's kind of neat for me. Okay, so basically I did the same thing here as I did here, right? This was the KSB of the calcium formation, calcium hydroxide formation. This was the amount of calcium given to start, and I'm solving for the hydroxide. So this is still squared like here, but now I just square rooted it and square rooted it. So I'm doing the same thing I did in the last one essentially, and it gives me 2.06 times 10 to the minus 2 molar. That's how much hydroxide I had to put in to initiate the calcium hydroxide formation.
Right.
Okay.
So then you put it in the OH.
So now I say, oh, that's the amount of hydroxide I have. So it's saying when calcium begins to precipitate, what is the magnesium ion concentration? So now I just take it back in here. So what am I doing here? I'm plugging in here and I'm solving for
the magnesium.
right?
Right. So
Does that
you're
make sense?
gonna have to square it then.
Yep. So there it's here, right? So I took this, I took this out. You see the square there, I square that, and now this is what I have. I plug in this number here to solve for that number.
4.85.
And I get 4.85, rounded off 4.9 times 10 to the minus 10 molar.
What?
So this is the amount of magnesium ion I have once I've put this amount of hydroxide into that solution. That's what that says.
And you're squaring it just because of the equation, right?
The sig
The
figs.
2 OH.
You said square, right?
Oh, yeah.
The OH.
So that's this.
Huh?
So KSB of this equals what?
Mg.
Mg, 2 plus,
OH minus.
And then OH minus.
OH
square.
minus
Minus 2
squared.
squared. Okay.
I just took it out from before.
Okay.
Remember, I had to put it over and then I square rooted it to get the concentration. Now I'm just putting it back here because I now know this one and I'm solving for this one this time,
Okay.
right? So I'm basically just putting in the same equation. Nothing changed there. Okay, so that looks like a fun example, good. Okay, that leads us into the complex ion equilibria. Okay. A whole lot of words here. How do I want to start this? Okay, I want to start this in a way that explains the differences to what we're transitioning out of and into. Okay, because there are some differences here. Here I'm looking at mostly cations that are in the transition metal range. Let me start with that. That means they have type 2 numbers usually and stuff like that. I'm taking that ion and I'm putting it into, say, water. And it could form what's called a complex ion formation. So I'm putting in something that's aqueous into something that remains aqueous, okay? Which changes what I'm doing here, because remember, this was a solid separating. Now I'm just simply saying, if I put something like silver ion into water, I now get something here where I get this, what I'm calling a complex, the 2, and that stays plus. I had 2 H2Os, complexed, connected. When I say complex, I mean connected, chemically connected.
Hydrogen bond?
To, let's not worry about how they're connected yet.
Okay.
I want to make sure this is clear what's happening. Connected to this silver ion. Okay? This is still usually aqueous. But when I put the silver ion into the water, I'm saying it forms its own complex. Okay? Then I could replace it with something else, like ammonia or something, and it will then also form complex ions with it. And some will form stronger ions and weaker ions accordingly. And we'll take a look at that. And that's the complex ion formation, or KF. So these are very strong. We can also add that, so in this case, the water molecules are acting as Lewis bases, but if I have something else that acts as a better, what is a Lewis base, by the way? Let's go, let me make sure that's clear.
One that can donate the pair.
Donates electrons.
Electron.
Absolutely, donates electrons. So if I had, so, and this, now you can think of your question. If I put in ammonia, is that a stronger Lewis base than
Right.
water?
Yeah.
And therefore, will it likely replace the H2Os here and form some kind of AgNH3 complex?
Okay.
Yes. They're all still aqueous. It's a very powerful and strong complex. But they also sometimes have color differences. So instead of a precipitate forming to see that difference, I'm now seeing it just simply with colors. So it's not a precipitate, it's just a color change. I think you guys are doing some of that kind of stuff now. Is that right? So you have something, but do you see, okay, good. Now, so that way I don't have to overemphasize this, but do you see the difference of what we were talking about to now what we're talking about? Okay.
Like, use copper there, yeah, no, iron.
So that's the transition into what I'm calling complex ion equilibrium. Whole bunch of junk here. By the way, you can also call this H2O, you just call that a ligand, something that you use in biology a lot, right? It's just connected this way.
Ligand, nice, that binds the,
This is the same kind of stuff. This is a stronger Lewis base. Therefore, it will replace it, whatever, same kind of stuff here, and you'll have something like this. So this is the same thing I was talking about here, where you have the H2Os with this silver ion in this, okay. We're not gonna get too much into, so one question it would pop up if I continue and don't say anything here, is that how do you know 2 or 4 or 8? How do you know how many are complexing? Okay. We're not going to get into that. It's a little more complicated, and there's not a lot of that's just based on experimental, right? But if you could figure it out, what would be the rationale for knowing how many would or wouldn't? So in other words, if 2 or 4 or 6, why is it usually 2 here? Let's say.
Based on the electrons.
Listen, I mean something even more simple than that. We don't have to get all to the detail of bonding. Why do things complex or not complex or whatever else?
Stability.
Stability, absolutely. It's most likely that this is just a more stable complex, meaning it takes probably less energy to hold it together. So it's as opposed to them being separate, which is probably more energy if they complex in this kind of format, then it's likely it's a lower energy complex, and therefore it's more stable that way, right? So within the environment it's in. So we're not going to talk too much about the specifics of how many are going to actually come here, but I just wanted you to be aware of that, right? So now I have that. I put this into, add in here. I throw in some ammonia, and I'm going to go 2 because 2 are going to replace 2 here. These are going to pop up in here, and then these 2 H2Os are going to come out. This comes out as a liquid. I have aqueous, aqueous, and aqueous, which means now this is called the formation of this. So I would use KF. What's the K formation of something like that? And that's what we're moving towards. Okay. So if I look at it from this perspective, this is really what I'm seeing here, right? If I go back, let me do one more thing with that back half. If I take this out and this out, there are 2 of those and 2 of those. Those are essentially just like what?
spectator?
Yeah, they're in a way they're spectating, right? They're not really. You're not losing any charges, you're not doing anything. If I just take them out, that's what I end up with here. Oops.
I like the idea.
I end up with that here, this out and out. And this is the actual
Your net.
K formation of silver complexed to ammonia. This is my Lewis acid, this is my Lewis base. This was a stronger Lewis base than water, which is why that occurred. And there's my complex ion.
So you just do net equation and work with that.
Use what?
The net equation.
Yeah. This is exactly what you need to determine. So is this going to be high or low? When you think, so KF, I'm referring to here, is the KSBs were all very what? Low. Because it doesn't take a whole lot to make them overcome that barrier and become saturated, right? And go into solution, come out of solution. But in this case, I'm putting ammonia into silver, which is just simply sitting in water. I've created this scenario that I told you where I have water now bound to that silver, and I'm calling that a complex. More specifically, I'm calling it a complex ion.
So in KF will also be
Okay.
lower?
And now I'm adding ammonia to it. The ammonia is replacing the silver, or the water, binding to the silver, and now I have this complex here. I just exchanged complexes. Is this going to be, do you think this is going to be a high K? So what would the K, let me go back. What would the K be here? I'm going to call this KF. This is the formation of this, so we'll call this KF. What would it be, high or low?
High?
High. What would it be? It would be this divided by the concentration of this squared and the concentration of that. Am I going to have a lot of this, or am I going to have a lot of this? A lot of this. K formation would be very high. KSBs were very low because only a little bit were ionizing. KFs, very high, right? Of course, this is one of those times where you're getting a chance to see where we're adding different things and seeing how they affect each other. Remember, a lot of Chem 101, it was just, let's just look at this thing and what happens? Water on its own, what happens? Now maybe I have sodium chloride in water, what happens? Right? Now I'm saying I could add different things, and I'm also making it more complex here. Different things are happening that we just ignored before and just said, oh, silver or ion in water is just an ion. Now I'm saying it's a complex. And now I'm saying if I add something else to it, I could create another complex, but you notice they're all aqueous, so these are all part of the KF. Right? The K, and the KSB, it was only the ions that were, because the other thing was a solid, which then therefore is just a constant, and that constant's wrapped up into that KSB. Right? And those are the things we learned about equilibrium constants in chapter 2 of this semester, which I think was chapter 15 probably, something like that.
Yeah.
Right? So keep those things in mind. That's important when you're now evaluating this. So here's my Lewis acid, representative of Lewis acid, Lewis base, and here's my complex ion. Okay. So here's what I was mentioning. So here's nickel. This, you see how there it's a 6. Okay, just going to take it as value. And when you have the nickel H2O6 ion, you see it's got green color. Okay. If I throw NH3 in here, that's going to replace the H2O. Why? It's a stronger Lewis base. And now I have this complex here, and guess what? It's a different color. This allows me to see the distinction visually. This is my indicator.
For the subscript for water and ammonia, are they always going to be the same thing? Like, because all the problems we've seen so far at 6 and 6 or 2 and 2, are they going to stay the same when we're actually writing out the equation?
For our purposes, yes.
Yes.
Does that in real life?
No.
They could potentially change.
Okay.
And that would just be because me. But when they do stay the same, what's presumed to be happening? That you can actually answer that question, right? They're binding to the same spots. The other thing is, what's the instinct? So this question's come up a couple times, so I might as well just touch on it. The main thing I want to do today is get through this chapter finally. I think we still have enough time, so I can stop it because these are good questions. I just got to make sure that we stay on track a little bit. What would you assume is happening here when you see Ni2 plus binding to 6 H2Os? What would you try to force there? How would you try to fix that? Where's Ni on here? Let's go. We don't do this that often in this class, right? And, see where we're looking at. We're looking at nickel right here. Okay. So that means that it's nickel 2 plus. So if I were you guys, and this is what I did when I was an undergrad, I would think a certain way, then I quickly realized I was wrong, but this is how I would have thought about it. Okay, I have 2 spots here to fill up what? The d orbital. I'd start thinking in that term, right? I've just lost 2 electrons, so I would expect there to be 4. If I were to just think about it in my knowledge base of how things bind. But that obviously doesn't fit here because there's 6. Right? Which is why I said we're not going to touch on it too much, because your current knowledge can't take you to this. But what I can say is you can figure this out experimentally, and then you'd be able to, then you would know what these are. And the presumption is somehow it's putting them in a way that would be more stable. Right? They're binding in a way that's more stable. And once again, when I do it that way, what's the fallacy of that? Why is that wrong? Because some of you are probably thinking, yeah, that makes plenty of sense. Why isn't it 4? What did I do there? I did that relative to the atomic orbitals in the nickel, right? When I'm sitting there looking at something, and that makes sense when you think of it that way, when you look at a very simple ionic compound or whatever. But I can also share things. It's sharing. right? That makes sense. And what happens when, let's see, some of us, I guess last semester we had, I didn't get a chance, I don't think, to go over this that much with you guys. But you have molecular orbitals, right? Remember those? You did have to study for them. We just couldn't sit in the classroom because of the fires, if you recall, last semester. But we did we get into molecular orbitals in class, or did I give you some worksheet to do at home?
You give it the worksheet, but then you reviewed it a little bit.
I got a little bit in. So what were molecular orbitals?
The pi bonds are the
Sigma and pi bonds, single and double bonds, right? And how the overlap between the orbitals of each of the atoms,
yeah.
how that formed and hybridized.
have
Remember the
one.
hybridization?
Right, the
So
one on
you're
the top
looking
and
at
bottom.
different factors in terms of how, if you think of this as a molecule, how this is forming. It's not just looking at the atomic orbitals off of nickel and then saying these would be the ideal spots for it. Okay. What happened, for example, with CH4 in that? Carbon has how many valence electrons? Where do they come from? Where are those 4 valence electrons at?
on the outermost shell.
What orbitals are they in?
Oh, that's it.
There, 2 of them are in where? The S, and 2 of them are in the
P.
P.
Mm.
Are those the same energy levels?
No.
No. Okay, and that's because that's how it sits comfortably. When it binds to 4 hydrogens, each one of those is binding to the 1s electron, which is in the 1s orbital of each hydrogen.
Mm-hmm.
How could I have a difference in energy levels between the ones that are in the 2s and the ones that are in the 2p's in those bonds, if those bonds are all the same? That was the hybridization idea, right? They hybridize into SPs. Remember that? So that's what I'm saying, is that you can't just look at it linearly the way you would like to, even though if you were to think about those things, that's the first instinct you should have, and then you could take it a little further and recall how some of the other things happen, and okay, maybe it's not so straightforward. And we're not going to worry too much about how these things do that. The main thing here is you could clearly see that there is a difference in color. Okay. Okay. Good. So I'm going to call this KF, and there's an example of KF. You notice now? Remember, KSB, this was a solid. KS, this is still in solution. That's aqueous. There's no precipitate out of it. Okay. Now here, okay, so here's a list of these. And you can see some of the metal ions here, the silver, complex to different potential Lewis bases, cadmium, cobalt, chromium here, copper there, copper here, a couple irons, mercury, nickel, lead, tin, and some zincs. Okay? And now what's the first thing you notice about all these KF values? They're all
Large.
really, really large.
Yeah.
These things form, they want to form. Okay. So that's the difference, that's completely different than the KSBs, which are just how many ions are leaking out of there. Right? This is like, these things are there and then ding, they're going to form really, really strongly. A lot of like, this is 10 to the 33rd here. Okay. And you notice that all the different things that do bind here, it's not just water or ammonia, right? I have here S2O3, whatever that is, F6, Br4, I4, CN is here, by the way, CN with cadmium here and copper here, okay? And so thiocyanate here. So you could look at some of these things and say, okay, you would need a chart to figure some of this out. Obviously, I'll provide you with the KF. But if I was to ask you about how certain things complex, then you just say, what would be the stronger Lewis base? Okay. So what do we have here? Very large. There we go. Just in case you didn't recognize that. It means it's favored. Love these pop-up things. They remind me of, like, you know, being in high school or something. It's not necessarily college. Okay, so we have an example. Okay, good. What is the concentration of copper 2+ ion in solution that was originally 0.015 molar copper nitrate and 0.1 molar ammonia? The copper 2+ ion forms the complex ion copper ammonia, copper 2+ ammonia, and it's got a KF value of this. Okay. We're on an exam. You guys have so many Ks. Got to understand what K and what you're looking for, okay? I want you to be able to think about it that way. You got to distinguish these things. right? Because unfortunately, I'm not there talking to you the whole time. I'm usually sitting here going, God, I wish you guys could finish this so fast so I can get out of here, because it's really boring sitting here. I'm not really monitoring you. I kind of have a confidence that you're doing this on your own anyways. So I'm just literally sitting here trying to stay awake. So the better you know it, the faster you get it done, the faster we all get out of here, and that's a good thing for everybody. So when you're on the exam, what am I trying to say here is that you want to identify what it is you're doing, right? If you can do that fast, then you can also more quickly get into the problem and solve it, right? So the first thing I'm going to say here is, what are a couple ways to identify that? Because when you get by the way, at this point, when you guys started in 65, now you're 102, these word problems are not as intimidating anymore, right? They really were in 65. You're like, oh my God, I got this thing and I got to figure it out. And then you slowly get better at it if you've progressed to this stage. The ones that didn't get better at it are still fumbling around lower, right? So at this point, you could now say, okay, I could read this and figure it out, but can I figure this out fast? Can I look at and identify things really quick? What is the KF? So, that's one way I could quickly, I'm looking at KFs. Oh, I associate that with complex ion, right? KSB, oh, I'm dissociating. Ka, oh, I'm looking at an acid. KB, I'm looking at the base, right? And remember, that was confusing, right? Because when I gave you the KB and then you have something for Ka, then you had to just convert that, right? In these cases, it's pretty obvious. You have KF, you're forming a complex ion. If you have KSB, which is why those things are kind of nice to know. Okay, so the first thing I say is I'm looking at KF. I'm trying to form something. So what's my equation? Cu2 plus NH3 gives me copper NH3, whatever, 4, 6, whatever it has, 2 plus. That's my equation, right?
So on the actual exam, are you gonna give us the chemical equation, or are we supposed to figure that out?
Yeah, figure it out.
Because like you were talking about, we don't know specifically how.
Oh.
how
The equation and formula are two different things.
Oh,
The complex ion.
The formula I'll give you.
you give, okay.
Yes. The equation, no.
Sorry.
Okay, no, that just make sure that's a common, that's right.
Because I was like.
You have it here. Yes.
Getting a lot.
And why does that matter? Of course, because you're going to have, so what would be the equation here? Cu2 plus what? 4 NH3. That's why she asked that. That's really important. Right? If you don't know this, then you don't know there are 4 of these. Your balance is different, therefore you're going to solve differently, because when you do your ice chart, the 4 is now relevant, right?
Yeah.
Okay, so that's why she asked that. That's absolutely, you need to know this. Well, I'll provide that as well. You need to know it, I'll provide it. You don't need to memorize it. I try to minimize memorization. Okay, so here's my equation, and there's the 4. Okay, so what do I do first here?
Then they put the KF.
I'm going to try, I gotta form this.
Okay.
Because it's not formed yet, right? I'm putting this here,
Yeah.
mixing it with this here.
Yeah.
And I have these concentrations, so the first thing is I gotta do an ice chart and form this and see how much I form. What am I gonna do there though? Because what's gonna happen is some of it's gonna come back. It's not all gonna, I'm gonna make an assumption here. When I mix these, I'm gonna get 100% formation here. So I'm gonna take away this back arrow. But I know that I'm gonna have some equilibrium. So I know then some of this is gonna go back here. So the overall equation is gonna look like this. But I'm gonna solve for this by assuming this is not here first, and then here going back second. So then this is kind of like the KSB, but not quite. Right? Some of it, not all of it forms is what I'm getting at. So I'm gonna say I'm gonna assume all the reactions combine to form this complex, and then some of that complex dissociates into ions. And this, if you put it into a real simple term, this is called the bounce back, right? Bounces this way and bounces back. Most of it's going to stay here, really high KF, but I'm going to have some distribute back out this way, right? And that's what I have in the bounce back is what's going to tell me my actual concentration of the ions and that at the end. Even though having said that, the actual concentration of this probably won't change too much, even though it is part of the equation, right? Because it's so strongly formed. But look at the KF, 10 to the 13th. That's really, really high. Okay. Bounce back. There we go. I think Dieter mentioned this Tuesday. So I was studying so hard and figuring out the bounce back is Other people told me it's really challenging. It's not. It's very simple. So once you see it in class, it should simplify itself, hopefully. Okay, so the first one is just this. I started with 0.015 and 0.1. Let me make sure that that's clear. That's coming from here. That's given. Okay, those are just the concentrations of the things given. No big deal there. There's nothing fancy about that. Okay, and then this starts at 0 because none is formed initially. Now there's going to be a change. So I look at the ratio here, and the change here, you could also just say, you know, minus x, blah, blah, blah. But since all of this is presumed to form in this complex here, then I look to see which one I have more or less than. I have less of this, so all of this will form. So this will all go, and that will become 0, assuming that I have 100% formation.
Mm.
This is 4 times this amount. That's how much I'm losing from here, so I still have some of that left. And then I start with 0 here. This is going to give me, this is a 1-to-1 ratio, so I'm just going to gain that amount of it. And that's how much I gain. That's 100% formation of this complex ion. And that's my first ice chart to solve this problem. These are the amounts that I have. Okay? Now I'm going to bounce it back.
In our notes, we have 0.
Doesn't took a minute, but they made a bounce back.
Your what?
A 0 instead of the plus 0.0.
It should be this.
Okay.
Because that's how much this is the change. So this changed,
Okay.
right? It had to. Otherwise, you don't get this. 0 and 0 would just be 0 there.
Yeah.
So this is 0 plus 0.015, which is just the amount there because it's in the 1 to 4 to 1 molar ratio within this balanced formation. Don't quite want to call it an equation per se, right? Wouldn't fit any of our actual chemical reactions that we learned in 101. Now, I just want to make sure you understand that that's 4 times. You guys got that? That's 1.1 minus the 0.06. That's where you get the. That's, you guys know that. It's no big deal. Okay. Now I'm bouncing. Second step. This is my bounce back. Okay. So I'm starting now with this and this, and 0 of this, right?
Mm.
So the starting amounts are just coming off of the ending amount of the last one,
Okay.
right? And now I'm going the opposite direction. Minus x plus 4x plus x. Right? Is this going to be very strong going back this way? Probably not. So I get 0.015 minus x, that's probably negligible. I get 0.040 plus 4x, that's probably negligible, but that allows me to solve for x in the amount of the copper 2 plus ion that I actually have in the solution. Okay, so then I put it into the KF formation. Okay, so I want to see how much formed. I go this, this, and this. I get 1 point, this was given, of course. Those things are negligible. And ultimately, my x should be very, very small, and it is 3.4 times 10 to the minus 10 molarity.
That is very small.
Right? Yes. As expected, right? Because most of it, that's the high formation. That's this here, given by that. So now, why are these negligible? If I take this and I subtract that, does that number change? No. If I add even 4 times that, does that number change? No. No. That's why you could just cut it out. That's the assumption method we learned a long time ago or something like that.
Mm. Approximation?
Yeah, approximation. Main thing is understanding what the relevance of doing that is. Let me see, what else could you guys potentially get confused on this? By the way, that seemed very hard for the bounce back?
No.
No, right? That's not hard at all. Right, bounce back, pretty easy. Which is good though, that's why you guys are in here, because that's the value you're gaining. Maybe it's hard if you just try to do it on your own. You're like, what's going on here? I want to just point out, I think if I recall, there's one nuance here that sometimes people get confused about it. I don't recall what it is.
Was it when it says in the question, it says it's originally copper to nitrate? Can you just ignore the nitrate in there?
Yes, why?
Dissociate.
The common ion?
Yeah, so nitrate would that be considered a strong Lewis base?
Nitrate?
When you, let me rephrase this. If I mix, say, hydrogen with nitrate, what happens? What's that called?
Nitric acid?
Nitric acid, and what happens? Complete dissociation. When I think of the and this is another interesting thing. I took you to saturation and whatever. Now I'm taking you back to solubility charts and stuff. Solubility charts, what's always soluble?
Nitric.
Ammonium, sodium, and nitrate was one of them. Potassium was one of them. They're right. So lithium, I think, was right. Most of them. So this is assumed to be soluble and not complex to anything at any level. Even more so in this particular problem, why is that not an issue at all? Because you already know what's forming, and this is the KF for that. So that implies all on its own that that has nothing to do with anything here, if that helps. So if you look at those things, that will help you kind of organize your thoughts there. Okay, let me then just rephrase or make sure this is clear. What I'm doing is I'm assuming it all goes here and then some comes back. That's the bounce, that's why I'm bouncing back. But I'm still using the KF. I'm not using something like the KSB here. Maybe that's something that sometimes people get confused by, potentially. So you're using the KF at this way, but you're taking the numbers from this and from that and plugging it into the KF for your final value. That could potentially be a component. These, by the way, what I just did, I only remember that from people coming in over the years asking questions about this. Because to me, that doesn't seem that much of an issue. But this is exactly what you figure out when you do the problems on your own. I do them in here, they look great, it's easy. Then you do them at home, and all of a sudden there are a couple things that you start thinking about that maybe I didn't mention, and that's where you overcome those things. Then by the time you get to the exam, you're like, oh yeah, you know exactly. You're not intimidated by those things don't confuse you anymore, right? But if you don't do anything prior to the exam, then of course on the exam, that's the first thing you get stuck on. You start doing it, and then you might say, oh, what do I do here? Wait, KF, how does that fit in? You hadn't thought about it, you haven't overcome that yet, and you don't want that to happen the first time on an exam, right? You want to do that at home, but when you get to the exam, it should just be a smooth, once you figure out what you're doing, then you just solve it. You make a mistake in the calculation, I take off a point out of 20 or 10 or whatever, no big deal, right? But if you have all kinds of mixed and matched ideas because you're trying to solve something in one way that you didn't figure out in time, make sure you figure these things out. I'm trying to point out all the things that you could come across, but I could miss one or two, is what I'm getting at, right? So make sure that you do a couple problems. These are not that difficult, but you could still come across some problems. That might be one of them. Okay. And now it shouldn't be, obviously, but okay. So would we have this here? Okay, good. So example 2. What's happening here? Let's just read it first and see what's happening. The formation constant, so once again, this is good. I'm looking at KF here, and I'm looking at the complex ion, HGI4 2 minus, and so Jenna should be happy we have our formula, right? Not too worried about it. And it's very high. Okay, if I didn't understand that this is complex formation, and I saw that number, then I would automatically think of K formation. There are a couple things you could look at here, right? That you could identify what you're looking at. So this says formation constant, but maybe that's an awkward way to state it. You're not familiar with it. It doesn't specifically say KF. But then you see what the K is. It's 1.0 times 10 to the 30th. You're like, oh, that must be KF, right? And then also, if you look over here, you could say, oh, well, that's kind of a weird complex. That must be one of those awkward complex ions, right? Because I wouldn't know how to put that together. And it's an ion form and whatever. Okay. So I know that. Then it's asking for what is the concentration of the mercury 2+ ion in a solution that was originally this amount of mercury and that amount of iodide ion.
The same thing.
Right? So what do I do?
Do you do your ice chart?
I assume that it's going to go what? 100%?
Completion.
Formation, and then it's going to bounce back, and then that bounce back is going to tell me ultimately what? I'll be able to figure out the mercury 2+ concentration. Okay. So I'll let you guys do that at home. This would be obviously the equation, and I'll just move this through. There's my bounce back, and I get the KF thing, and then the HG, and we'll move on. Okay, you have one extra problem to do. One less thing we got to do here because it's exactly like what we just did. But this way you get a chance to try one on your own. Does it have the answer there?
No,
Yeah.
in the back.
In the back, so you have the answer, but you don't have the solution?
Yeah.
Good, okay, perfect. So then you could mix and match. If you have any problems, send me an email. I'll send you something back. Okay, moving on. Let me see, what do we have here? Okay, so the most common Lewis bases that increase the solubility of these metal cations are ammonia, cyanide, and hydroxide. Okay, and then they give you examples. So that's just a simple statement. Those three things are stronger Lewis bases that will pull the complex ion to them and away from, say, water, if that's what you're starting with, right? But presumably, I can start with something other than water, and then these things should be able to go in there and pull it away from that as well, if you had a complex ion formation to begin with. Okay. So I guess what they're getting at here is okay, if I look at it that way, what if I look at this thing here? This is in water, so I have silver chloride, and then I get this small amount of iron. So what would this be called here?
KSP?
KSP. Okay, so that's something you could quickly say. Now it's saying, what if I put this thing here, this is in water, and I added, let's say, some cyanide to it? What would happen?
It would bind to the agent.
The CN minus would do what? Bind to the silver.
Silver.
And then what does that mean? It pulls this out, and then what happens?
Or
That
the
means it would
formation,
then
the KS.
shift this through Le Chatelier's principle,
Right. To the
right?
right.
I shouldn't have to tell you this one anymore. If I'm pulling something out of this, it's going to shift it that direction.
Right.
And so I'm going to lose more of this, and I'm going to form more of this, so what's going to increase there?
So yeah.
Cl minus, right? Unless I exhaust all of this, then it will reformulate whatever its equilibrium is. Or if I put so much of this in, it could potentially just pull it all over. And so any of these three things would potentially do that. That's probably all. So the KSB for this is very low. And what would happen now if I did add this? Would the KSB be higher, lower, change?
Oh, go
Oh, it's going to be lower.
lower,
No, higher.
It's a good thing there are only A and B on this one, right? It's
Yeah.
50%.
It's higher. It's going to be higher.
You're
You're going to require more of this. Yeah. Higher.
Could there be another answer to it?
Yes.
What would the other answer be? Higher, lower, or what? There could be one, right? The same. That could be, so you have 3 chances.
I said higher because it's less concentrated, the solution, if you're taking out the silver.
Would the KSB change?
It's the same.
Probably stay the same. Why would the KSB change? If I put in enough, I'm going to pull some of this out
Right.
from this, but this association is going to stay the same, which is what the KSB is, right? Would it change the concentrations? Yeah. Right? And hence another difference to help you out on that distinction a little bit, right? Okay. So, let's see, where are we going to with this now? NH3 increases the solubility dramatically because ammonium forms the complex with the silver ion, which is this, right? So once again, we changed molar concentrations, but the KSB would stay the same within that whole thing. And now if I pulled it all out, then I would end up with no KSB because I would lose all of the solid at some point if I put it all. So you got to understand what's happening in each part. Okay, so anyways, here, let me go, okay. The association I think they're trying to make here for you is this. This is really, really low. And this is going to be, which one are they put? Let's put in any of these. The formation of this would be what? Really, really strong, right? Right. So these are going to grab these at a high rate and pull them out, which then therefore would shift this, if that makes sense. But if the association of any of those 3 things were not that strong, then you would have to have a certain amount of them to have that, for them to be pulled out, right? I think that's what they're trying to get at here. That's why they're showing you how high this is actually a lower KF than some of the other things we've already seen, right? But it's still extremely high. So that's all that's happening. These things are pulling the silver out, you get this, so the large KF value significantly lowers the concentration of the silver plus ion, and therefore drives the reaction that way based on Le Chatelier's principle. Whoops, looked by so fast. Does that make sense? That's what I started. I told you all this, but here's sort of their way of showing it. It's okay? So, two reactions can be added together. I have this here. Once again, they're calling these reactions. It depends how you want to call these. That's a loose term now, right? We've loosened that term up. I've never fully formally said that these were chemical reactions, but that's what a reaction is. These do not fit any of the traditional oxidation reduction reactions or exchange of ions, right? This is just dissolving or not dissolving, forming in some way. So maybe this one is a little bit more like a chemical reaction because it forms a complex, but this one is just dissolving, essentially. So keep that in mind. I'm calling them all reactions just so that we have a shared term here, but you could debate that. So here I have, this is my KF from this reaction here, right? So I have, I'm starting with this here, I'm ending with this part here and that there, and I'm adding the NH3 in between. Okay. So I have this plus this gives me that.
Okay.
Right? Everybody agree with that?
Yeah.
If I can cancel out that silver and that silver, I'm left with this, 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 and that, right? I just cancel out, hopefully they do that for me here. They do it? Oh, good. Okay. So the multiplying these two things together give me this, right? Or adding them. But what if I want the overall K of this, what do I have to do? I have to multiply those two together. And that just gives me the overall equilibrium constant of this here. And what is this? This was something that had a KSB. I added something to that, and I gained the KF value of that. So the KSB times the KF to give me this overall equation here is going to give me my equilibrium for this equation. KSB times KF.
And you just call it K, you would call it.
Just call it K.
Like the beginning.
Yeah, just call it
equilibrium.
I mean, if you could, you know, here's one thing, this is interesting. You could put your own spin on it if it makes you more comfortable. So if it was me and I was like, okay, I'm a little uncomfortable with that, I might call this KSB/F or whatever. You could make something else that just makes sense to you, right? Or you could just leave it as K.
KN.
It's just the equilibrium for this equation, which is a combination of these two. Is that okay? Okay, so that's how you can solve for that. Okay. Okay. This is kind of saying the same thing again, right? If I have this, if I just have this in a container, what am I going to see primarily? What's it going to look like?
If you just have what?
Just the top, just the green equation.
Oh, just aqueous.
I'm going to see a cloud, right? A white cloud in the water. What if then I add this to it?
There's completely different color.
It's gonna just clear it up.
If you add.
It's going to clear it up.
Yeah.
Yeah, Taylor, you're saying the right thing.
Because NH3 is aqueous.
It's going to get rid of the cloud.
Right.
It's going to dissolve what is considered the cloud into something that is now a complex that's not a cloud and it's not a solid anymore. It's part of the, so that's all they're saying in this thing here. They're just showing it to you. Here's my cloud, right? Silver chloride and water. So I'm going to have a few ions in there, but very, very few, right? If you think of the KSB. And now I'm going to throw some of NH3 or CN or whatever in here, and look what happens if I throw enough of it in. It gets rid of that.
Put it to the cup.
And that's exactly what we just saw in those two equations. But that's a physical representation of what's happening.
Mm-hmm.
That's pretty neat, right? How you can do stuff like that. So this one is probably ammonia they added because that's something more common, but if I put cyanide in there or if I put hydroxide in, it would probably do the same thing.
It's like when we had the copper hydroxide or...
Copper hydroxide? Yeah.
And then we added the HCl, I think it was, we were able to get the copper alone.
Right.
So you got the blue color.
It's also this. I mean, it's one of those things where you just look at what you have more of and what's happening as a result. So when you guys did the, I use this example a lot because it's easy to see. when you added too much base to your acid with phenolphthalein, it turned pink, right?
Right.
And then it got too pink and you're like, okay, I'm not right. At that point, you didn't understand what you're doing, but you're like, it's just not right at that point. Now you guys exactly know what's happening with the phenolphthalein, right?
Yeah.
You could define which, which indicator would be better. But then for some of you, I said, okay, if you want to get it lighter, what can you do?
You just added up the
Add a little bit more of the acid back, right?
Yeah.
And just calculate how much of that acid you add and add that to the total
Right.
of what you started with. So now I have how much is each drop, and then each drop I add back to get to that lighter pink. Once again, you could reverse these. You could reverse what you see based on how much of something you have. So obviously, I can put enough NH3 in here where only part of this goes away, or enough where it all goes away. If I add more silver chloride in here that overcomes the NH3, I can get some more cloud back. Right? It's just a physical representation of exactly what those equations are telling us. And that's maybe how we know those equations work that way, right? That's the experimental procedure that was shown.
NH3 is a weaker base than NH2, correct?
You're comparing ammonia with
NH2, which is,
NH2 would also be charged, right?
right,
Would be charged with a minus.
right, 2 minus.
Yeah.
Oh, yeah, minus, yeah.
Yeah. Okay. So generally a slightly soluble salt, precipitate, whatever, the same. That's all the same. Nothing big there. You guys can read that if you're interested. Okay. Now, this is one of those things that you guys are doing. I think you guys are doing the qual now in class. Okay, so you take a couple of these things here, and then
Oh,
you
yeah.
precipitate one, you centrifuge it down, you precipitate the next one, and that's based on the same.
I love that one.
Yeah, so this is pretty straightforward, and we've already discussed how to do this, right? That's what we started today with, that precipitating. We just had 2, so that's
The
no big
amounts,
deal.
yeah.
Okay.
Like how much of the hydroxide?
What do we have here? When added to water, would most likely increase the solubility of copper sulfide. So copper sulfide, okay, so the very first thing I read here, what I read, and this is important, I would say that this is a solid, okay? I might not have a solubility chart or anything, but I'm asking for the solubility of this and how to increase it. Then I say, okay, what am I trying to make soluble here? The cation or the anion? Cation.
Cation, yeah. That's what
Complex
anion.
ions were based off of mostly the transition metal cations, right? That's what formed, because those were acting as what? Lewis acids. And therefore the stronger Lewis base is what pulled that out, right? Okay. And it pulled it out because there was this limited equilibrium that we called the solubility product, or KSB, that we saw. That's how, otherwise if it was complete solid and I didn't have that equilibrium, could I pull any of this out? It's not pulling it out from the solid, it's pulling it out from the ion, right? And that's why it shifted that equilibrium away. Okay, just keep that in mind. So here I'm saying, I'm presuming I'm looking at the copper, and I'm saying which one of these anions are going to pull that off. And we did have a list of 3 things that were pretty strong acting Lewis bases. What were they? Ammonia, cyanide, and hydroxide. Do I have any of those in here?
Yes.
Where? Ah, that must be it, right? Okay. No big deal. Right? If you break it down appropriately. On an exam, all of a sudden that question becomes really challenging if you don't understand, right? If you didn't know certain things. So, and I won't give you anything that you wouldn't know, obviously. It'd be something like that. Okay. What do I have here? KSP value for this, KF value for this. Calculate the overall equilibrium constant. Okay, that should be pretty straightforward. Okay, there's this, there's that,
Put them together.
and there we go. Okay, I don't need to show you any more than that, obviously. You guys can take pictures or whatever, but that part should be okay, I hope. Now, in the interest in time, I'm going to move through this and get to, I think there are only 1 or 2 more things I want to discuss. Okay, solubility of amphoteric hydroxide. So the very first thing is solubility. We're talking about things that will dissolve, okay, at some concentration relative to some volume. And the thing we haven't really discussed here, but I keep adding, which is an important element, is temperature. Okay, temperature does not. And the next thing here says amphoteric, and then hydroxides. So I'm clearly talking about a hydroxide, something with an OH. What's that other term? And I've presented that term before. Yeah.
The base and the
Yeah.
It could act both ways. Where did we first see that? Water, absolutely. Where water could act as an acid or a base? Amphoteric. Okay, so now this topic should be pretty straightforward. Just looking at it, reading it, if you understand it, then you already know what it's about. So I'm looking at metal hydroxides that are insoluble or slightly soluble in pH neutral water.
So
What if I put that in an acidic solution, and what if I put it in a basic solution? That's what it's asking. Okay, what will happen? So I'm looking at aluminum hydroxide here with the KSP that's very, very low, but I'm still going to have some hydroxide and some aluminum. If I put this in an acidic solution, what happens?
It's gonna make water.
It's going to make water.
Yeah.
Right. So it's going to shift it and make it more soluble too, right?
Uh-huh.
Because the same rationale we just used.
Right.
Make sure this is clear. I'm going to take aluminum hydroxide. What do they have here?
3.
3?
Yeah.
Okay, so this is just a simple,
Plus H.
they're saying it's already in water, and they're saying it's a solid, right?
Mm.
We know we're going to get some of this kind of stuff here. This is a ionic compound, and I'm going to get this here. Okay.
Yeah.
I add H3O plus, whatever, HCl, whatever I want to add. And let's just do this. This is going to bind to some of these. This is going to form H2O, so that'd be 2 H2Os per each one, right?
Right.
It's going to pull this out. It's going to shift that. It's going to make this what? More soluble.
Right.
Yes. Right? And that's those are the kinds of things that are going to happen here. Okay. So basic anion, that's this thing here, more soluble in acidic solutions. I just explained that here. Okay, there's our pseudo acid. Doesn't matter what it is, HCl, H2SO4, whatever. And then, okay. So now I have this. I dissolve it in the acid, and I get this. So that's basically here, right? That's everything we just did.
Into the acid. Yeah.
It's just put into the stoichiometric ratios. So simply saying that if I, now, with what we just looked at before, see this is a solid here. And I'm taking this and I'm just adding the H3O pluses here. Okay? And then these are just neutralizing these, and I'm getting this, which is essentially the same thing here. Is that, everybody understand that? That's the same thing?
Yeah.
Okay. Okay. So this acts as a base, right? Because it neutralizes the acid. Now, here, in this case now, I'm going to do the same thing here,
You're gonna add
but now I'm going to add a base.
NaOH.
So I'm adding now just OH. I could put it as NaOH, but let's just add it as, you know, the thing that's going to react here.
Okay.
And what this is going to do is this is going to form another position here, and I'm going to end up with the AlOH4. And of course, the minus carries over from the minus here.
Right.
So I have a different compound. So what's happening there?
It's just making it more basic.
It dissolves in the basic solution. Okay, let me rewind. What are we trying to do here? We're putting this thing,
Okay.
which has this whole equation here, into an acid or a base.
Mm-hmm.
The acid part is pretty intuitive, right?
Right.
It just pulls that out and shifts it. The base part, if I put it into a base, it's going to bind to this thing and form this.
Take away the solid, yeah.
So it acts as
One base.
an acid. It's neutralizing the base. Not in the traditional sense that you would think of as forming H2O, but it's pulling the hydroxide out of the solution, which therefore reduces the basic component of the solution. Is that okay? Everybody see that? Okay, good. So that's the amphoteric. It's acting both as an acid and a base under that guideline. So if I look here, I have the aluminum reaction here. So here's the aluminum hydroxide, and you notice here, what?
Oh, this is a cloud.
That's the precipitate
Right.
here. Then if I add it to an acidic solution,
Hydronium.
I form this thing going on over here, right? The acid here will now bind to some of these things, pull them out, form this, and I'll get more of this. And you see, if I put it in enough, it all goes away here. Inversely, if I put it in with the base, it forms this. What is this called? What complex ion? Thank you. We just got done in that section, right? And as a complex ion, is that dissolved?
Yeah.
Yes. Once again, clear, no more precipitate. Acts as an acid and a base, depending on whichever one you put it in. Hence the term amphoteric.
What would you say experimentally would be your thinking process as to which way you should go?
It depends what you want to do. You got to have an objective, so it all depends on your objective. I'm just pointing out what would happen if you did this or this. Based on whatever experiment you're doing, then you say, okay, what do I need to do? I want something in basic or acidic conditions.
Gotcha.
So just to finish up, a couple quick things. So in addition to aluminum ion, other cations that form amphoteric hydroxides are chromium 3+, zinc 2+, lead 2+, and tin 2+. Okay? These things you should know because they act in both of these formats. Other metal hydroxides such as calcium, iron 2+, and 3+ are non-amphoteric. They just become soluble in acidic solutions. Why? Because they don't form what?
Complex ions?
The complex ions is readily, yes. That would be the rationale for it, right?
Okay.
Okay. And with that, I think that then you guys do this qualitative analysis thing, which you're already doing in lab. So you could look at the notes, but I'm not going to cover them. They're essentially the same thing we've been talking about on how to take something, precipitate one thing out, spin it down, get this collection, decant, then put more whatever, take something else out, decant, spin down, decant, you get something else, and it's just a way to separate things. Okay? So with that now, on Tuesday I'll give you a take-home exam that you'll have all week, and you can turn it in the following Tuesday. Okay, or take-home homework kind of thing that we talked about. And we'll get into chapter 18. I think it's thermodynamics. We'll get into that on Tuesday. We have 3 weeks left, 2 chapters, electrochemistry and thermochemistry. We'll talk about things like Gibbs free energy and spontaneity, along with delta S entropy. For the next chapter, and then the last chapter, we'll talk about locomotive forces and things like that. They're about 100 slides each, so hopefully I can break that up into 3 lectures for each of the chapters, which will finish up the semester, and then you'll have everything that you need for this class. Okay. Okay. Have a good weekend. I'll see you guys next week.